Questions about anything from last time? I realized I never wrote down the definition of a way to parametrize a line in the complex plane. There it is, the obvious thing to do. Kind of like vector parametrization in the plane that you learned in sophomore calculus. Let's see, there are some other facts I didn't mention last time that I kind of left implicit. One is that the definition of the complex integral doesn't depend on the way you parametrize the curve. That's the same. The proof of that is just the R2 version. We can write out our complex integral in terms of real integrals, and of course the reparametrization theorem holds for those real integrals. So it's elementary to check that fact, and you can read it in books rather than waste time in class here. Another important thing is that when you integrate backwards along a curve, you get minus the integral. That would be obvious if you were looking at Conrad Knopf's definition of the complex integral as a kind of a Riemann sum thing, because then when you go the other way, those delta z's would be minus what they were going the reverse direction. So that makes it kind of obvious from a point of view of Riemann sums, but you can prove it based on multivariable calculus also. Let's see, so if z of t, if the parameterization is z of t as t ranges from a to b, then the minus gamma would be parametrized by, let's see, what is it? Minus gamma would be going backwards. So you'd start at b and you'd have t times a minus b. That would start at b and go to a as t ranges from 0 to 1. Anyway, those are easy to check. A thing to note is that I didn't say it, but I should have. We assume the z prime of t is not equal to 0 on the parts of the curve, piecewise C1 curve, where it's C1. We should have done that in the definition, because it'd be kind of silly to have a parameterization where you stop and just sit there for a while, or maybe turn around and go backwards and then go forwards. That would be kind of crazy. So that's a natural thing to do, just like you do in the sophomore calculus. Questions about anything? So today I'm going. The topic is Cauchy theorem on a convex open set, which is amazing that I can get to it so quickly. The key to this thing today is the Gorza lemma. It's going to make this pop out in kind of a mind-blowing way. So let me state what the big theorem is today. Suppose omega is a convex open set. Could somebody close that door? In C, and so the theorem is, I'm going to cook up, this is not the Cauchy theorem, I'm going to cook up a complex antiderivative. Oops, wait a minute, this is the Cauchy. Okay, I'm supposing it's a convex set. I'm supposing that f is a function mapping omega into C that's continuous. On omega. And we suppose that P is a point in omega, so this is going to feel like the Gorza lemma. And F is analytic. on omega minus p. So there's this one annoying point. It'll pay off to have that point around when we do the Cauchy integral formula. Then the big conclusion is that the integral around a closed contour in that convex open set of f is 0 for any closed contour curve gamma in omega. Okay, that's one version of the Cauchy theorem. I guess if I was going to call this the Cauchy theorem, I would say that omega is a simply connected domain. Okay, a domain is a connected open set. And simply connected means it has no holes. So holes is a problem. Anyway, today a convex set can't have a hole. Okay, the proof is a beautiful thing based off the Gauss lemma. And so let's see. Here's my convex open set. I'm going to pick a point in the convex open set, A, and I'm going to take a line that starts at A and goes to Z. Now let's see, this is my omega. This is thing. So that's being convex means if I stick 2 points like A and Z there, the line connecting them is contained in the set. That's what convex means. Okay. Well, the plan is I'm going to cook up an antiderivative of little f. Plan. Cook up a complex antiderivative of little f on omega, i.e. an f such that the complex derivative exists and it's equal to f. Okay, now notice that little f is continuous. So if I had such an f, the derivative would be continuous. And that was a good thing. So that if I had such an f, so note, if we had f prime equals f, continuous would mean I could use the fundamental theorem of calculus. Number 2. Okay, and what that would mean that I could do something like this. Integral from a to z, not a to z, L a to z, the line that starts at a and goes to z. So I'm thinking of a as fixed. So I'm going to fix the a and hold it constant. I have to put L dw right here, f dw. Well, that would be the integral of a derivative. And because the derivative is continuous, I had to assume that when I was proving the fundamental theorem of calculus. Okay, that would be f at the end minus f at the start. And the aha moment here is when I differentiate this, f of a would be a constant. So if I take d by dz of that equation, I would get d by dz of this integral. It's kind of like freshman calculus and the fundamental theorem of calculus, except this is a complex integral. That would be f prime of z, and that would be little f. So the key is going to get this capital F. So the key to getting this antiderivative is to get the capital F. And look, let's see. It's the derivative of this thing. So the big idea is to define. So the big idea. Define f of z to be this integral. Okay, of course that's well defined, but I fixed my point A and I've got a line. If that was an arbitrary curve, I'd have to show that that's well defined. But since I'm using a straight line there, it is well defined without messing around. In future iterations of this theorem, we'll have to do something there. Okay. The next step, I want to show that f prime is equal to little f. And the key is going to be Grzaz. Okay, so let's draw a picture here. I'm going to take a... Uh-oh. Heck. Okay, sorry. Let's see, I'm going to have LA of Z. Here's A. Let's call this point Z naught. Let's call this point Z. I'm going to go A to... I'm going to make my... So this is going to be LA to Z naught. This is going to be LA to Z. And let's see what's the natural thing. I'll take this here to go like this. This one is going to be L Z naught to Z. And I know that the Grzaz tells me the integral, it doesn't matter where the stupid P is. P could be inside this triangle or outside or someplace. So I'm not even going to think about P. And let's see. What does Grzaz tell us? If we go around this triangle, we get 0. Okay, so let's go around the triangle. I'll go... so Grzaz says... integral, I'll go A to Z naught plus the integral Z naught to Z plus, I'd have to go backwards, integral minus LAZ. I'll use this, my own personal notation here, like that, to be a sum, to save the writing. And as I mentioned in the beginning class, going the opposite direction along that one is going to make this minus the integral along A to Z of f dz. Okay, and so let's see. That's a big fat 0. Okay, and this integral from A to Z naught is capital F of Z naught, and this other one is minus capital F of Z. And when I put that on the other side, I get F of Z minus F of Z naught is equal to the integral from Z naught to Z of f dw. Let me move this over a little bit. And now, what do I want to do? I want to divide by Z minus Z naught. So I'll have a difference quotient to mess around with. And so we expect that to be equal to f, to tend to f prime of Z naught. And so it's going to be kind of like freshman calculus, proving the fundamental theorem of calculus that's going to work out. Let's see, what do I want to do here? We expect that it tends to f prime of z naught. So that's kind of a remark. Okay, well, can I make f prime of z naught look like that thing on the right? And so here's a little baby fact.
I'm a little confused. Which part of this is going to be approaching f prime of z naught?
That difference quotient. Oops, not f prime. F of z naught. We're expecting f prime to be f. So a baby fact that I'm going to use to make this relatable to what I want is that if I integrate a constant along a line from z naught to z of c dw, that would be equal to c times z minus w. You can calculate that with your bare hands, or you could use the fundamental theorem of calculus that the integral, let's see, c is d by dz of something. So the antiderivative would be c, d by dw, rather. D by dw, c times w, dw, and that would be cw evaluated between z naught and z, and check. That's what it is. C times z minus z naught. Okay. And so if I let c be equal to this constant, f prime of z naught, then, so, let's see, what do I want? F prime of z naught equals 1 over z minus z naught times the integral of the constant. Line from z naught to z of constant f prime of z naught dw. Okay, and so now when I define, when I take that difference quotient there and subtract f prime of z naught, so that's the difference quotient minus f prime of z naught equals, let's see, a 1 over z minus z naught integral from z naught to z. Let's see, the first one says that that's f. The difference quotient, it's just an f there. And then this one is a constant. So here I'm going to have f of w minus f prime of z naught, that's a constant, dw. And of course, this is an integral along a small thing of a small function. So it's going to be so small that that thing out in front is not going to mess with it. This is the important moment. Is that any questions about this?
Why are we talking about prime again?
We want to differentiate f. We're not talking. I shouldn't be saying that. Why the heck? Did I do that? Where did I start doing that? Thank you for catching. What the heck? Dumb. Okay, now I'm getting somewhere.
One more.
One more?
No, the left side of that equation.
That would have been a true equation before. Still true. Okay. Sorry about that. Anyway, I want to show this goes to 0, of course. And the way to do that is to just use the basic estimate. This is less than or equal to 1 over z minus z naught times the max of f of w minus f of z naught. On the w would be in the trace. So I'll abuse my notation and just say in the curve, when I really mean the trace of the curve. So that's the basic estimate. The mass times the length of the curve. And of course, the length of that line segment is the scary thing in the denominator there. And so that cancels the scary thing. And this can be made less than epsilon using continuity. So I can use continuity there of the little f. Questions about that? So sure enough, that difference quotient goes to what I want it to be.
So it's a little overkill, but you could say this follows from Dirichlet differentiation.
What?
You could say this follows from Dirichlet differentiation.
Don't have to use any Lebesgue facts about
Right,
Lebesgue. I mean, this is just basically continuous functions and taking the max and Riemann sums.
Right. So I just saw the average over integral is equal to f of c. So it's,
Yeah, I don't want to overkill it. I want to underkill it.
that's what
Yeah, it's amazing we can do all this without messing around with subtle questions about real analysis and worrying about convergence of integrals. We're always going to use uniform convergence of continuous functions rather than any fancy measure theory. When you start blending in measure theory, you get some really fascinating questions and problems to think about. By the way, this works every time, so there's a corollary. Analytic functions on a convex open set have an analytic antiderivative. Analytic functions on a convex open set have analytic antiderivatives. Given by that integral. Line integral from a to z of f dw. So analytic functions f a is fixed in omega. Let's see. I haven't proved the big theorem yet, have I? Oh, I guess I haven't proved the integral around a closed. So that's a corollary. And now back to the proof. Of the Cauchy theorem. Let's see. We have f prime of z is equal to f of z, and f of z is continuous. So now the big moment that looks like it might have been hard is simply that the integral around a closed contour of f dz would be the integral around of f prime dz, and f prime is continuous. And so I can use, this would be the f at the end minus f at the start. And of course the end is equal to the start is when that's closed. Equal when gamma is closed. And so that would be 0. So I just proved the Cauchy theorem by coming up with an antiderivative. Okay, question?
Yeah, why did we have to do all this, why did we have to do all this work to say that, this function defined as the integral of the function, that the derivative of the integral is just a function inside the integral?
Well,
Is it just because it's...
the Cauchy-Riemann equations are relevant here. And so it's not just true for any old function you can stick in there. I mean, all the definitions here, the complex integral, the complex difference quotient, all different than freshman calculus. So we got to work to show this.
So it's because it's a function of a complex variable.
Complex variables, the meaning of these symbols is now something quite different. Very natural. I mean, you can think of them in terms of Riemann sums. So it's a very natural extension, but you got to check all that stuff. Yeah, question.
Can you summarize what assumptions we had for the existence of a antiderivative in this case?
Well, the hypothesis, I could have the f is continuous on the whole domain and analytic except maybe at one point. That was the assumption back there.
And then were there assumptions on the domain? Or it's just like
Convex open. Yeah. In the future, we'll do a simply connected domain. In fact, soon. But the mind-blowing thing is that once you have this Cauchy theorem, we can get a famous Cauchy integral formula. And just having the Cauchy integral formula on the disk is going to get us a lot of miles. But let's see. First, I'll state version number 1 on a convex open set. Let's see. The key here is to write. Let's see. I want my f of. I'll call it a g of z here. G of z is going to be equal to the difference quotient. F of z minus f of z naught. So z naught is an omega over z minus z naught. That's if z is unequal to z naught. And then f prime of z naught if z equals z naught. And now you've been wondering why the heck I have this stupid point p floating along, and it never interferes with anything we're about to do. This is the function like I've been saying we have. This is continuous on the whole domain, so that this. So we're assuming here that f is analytic on omega. And so this thing is analytic on omega minus z naught. And because f is analytic, f is continuous. Not f, g. Let's see. So this thing is continuous. G is continuous at z naught. So G is continuous at z naught. So it's continuous. So continuous on omega. And this G, little f is analytic on omega. This G is analytic on the punctured thing. And it's continuous on the whole thing. And so my Cauchy theorem on convex means I can apply that Cauchy on convex is going to tell me that the integral of G around a closed contour okay, let's suppose that Z naught is not on gamma. So here's the case. Z naught not on the trace of this closed gamma. Gamma needs to be closed. Well, then what do I get? I get the integral around gamma of f of z minus f of z naught over z minus z naught. Since that's what g is on gamma, since z naught's not on the curve. So this would be a dz, and that would be a big fat 0. And so what I would get here is that the integral of f of z over z minus z naught dz equals, and I put that on the other side, integral around gamma f of z naught. I can pull the f of z naught out front of 1. It's a constant. I can pull it outside the integral. That's something you need to check. Okay, and this is a famous thing. That's called the index of the curve, and that just turns out to be a number. In fact, it's the number of times gamma winds around z naught. Okay, so if I divide both sides by 2 pi I, divide by 2 pi I, then you get that f of z naught times a thing called the index with respect to gamma of z naught is going to be equal to 1 over 2 pi I integral along gamma of f of z. This is the Cauchy integral. Famous thing. So if the index were something I could compute easy, which usually you can, it's an integer. And if you can compute it, that means the value of an analytic function inside a curve is something you can determine from an integral. And that's a mind-blowing thing that has huge implications. Okay, this thing right here is called the index. Yeah, so that's the index of a curve. It's also called the winding number. Index or winding number. Don't worry about this today. And it's 1 over 2 pi I integral 1 over 1 z minus z naught dz around gamma. So let's see, I'll show you a winding number. Here's z naught. Here's a curve that goes around twice, once, twice counterclockwise. The index of that curve, its index of z naught is 2. It winds around twice. Question? Javier.
You may have went over this, but can you go back to a little bit up? When you get the f of z naught out of that integral, why is it z naught?
Because that's a constant and I can pull it out. So first I move the minus to the other side, so it's a plus, and then I pull it out the integral because it's a constant.
Okay, thank you.
Yeah, I guess that's something you need to sit down and check at some point. Okay, that's a general Cauchy theorem, but now I'm going to do an easy one where I don't have to think so hard about the index. So here's the Cauchy theorem, Cauchy integral formula for a disk. Okay, so here's my picture here. I'll have this circle. Okay, I'll call this C sub r about z naught. That's a circle. Z naught's the center. and I'll have a point A here in the circle, inside the circle. And I'll have a bigger disk. So here's the bigger disk, D capital R, about Z naught. And I'm assuming that I have a function that's analytic on the bigger disk. Okay, so the assumption is we assume F is analytic on the bigger disk. And I would have 0 is less than little r is less than capital R. And that C sub r needs to be counterclockwise. So let's see, the C sub r is the counterclockwise thing. So that would be parameterized by Z of t equals Z naught plus R e to the it, as t goes from 0 to 2 pi. That's counterclockwise. And my point A is in the disk of radius little r about Z naught. Then the famous Cauchy integral formula for the unit disk is f of A is equal to 1 over 2 pi I integral around the circle of radius r about Z naught, f of z over z minus w Z naught dz. That's a mind-blowing thing. That means the values inside a circle are completely determined by the values on the circle. That's a really weird thing to say. I mean, it's like, what the heck? Turns out that harmonic functions are going to have that similar property. It means, like, if you know the temperature on all the walls, you can figure out the temperature inside. And that's exactly kind of what this is related to. Temperature, steady state temperature behaves like that. If you know the temperature on the walls, you can figure out the temperature at any point in this room. That's going to be true about harmonic functions in general, which can represent steady state temperature. And it also means that you can't mess around deforming analytic functions. If it's known on that circle, then it's completely determined inside, and you can't like push it around and deform it like you can a continuous function or a differentiable function. That's weird.
Excuse me?
Yeah.
I may be missing something here. Is there a relationship between A and R?
Oh, for crying out loud. Yeah, so let's see. When did I start? Oh, Z naught's the center. This should have been A. CR? What? No, this is a CR Z naught. That's correct. Yeah, Z naught's the center, and A is a point inside. Okay. It's still mind-blowing that this is a true thing. Okay, so a little lemma. Let's see. So I showed you how we are going to apply that Cauchy integral formula. So here, the y here is a little lemma. The index, if you integrate around a circle, and right here, 1 over z minus a dz, that's equal to 2 pi I when a is inside. And it's equal to 0 if a is outside. Of course, that's just the Cauchy theorem.
And do you need that denominator to be squared then?
No. by Cauchy on convex. So when A is, what am I, yeah, this is true. Okay, so when A is outside, that's an integral of a analytic function around a closed contour. So we can use Cauchy on a convex on a bigger disk and get 0 there. But when A is inside, there's a singularity inside, and you can't use the Cauchy theorem because it's not continuous at A, it blows up at A. So that's weird, that's bad. You couldn't use Cauchy because of that. In fact, you can, yeah, okay. So let's see, let me check so let's do step 1 here, the proof of this little lemma. Let's write h of A is that integral. Okay. Let's step 1 is to calculate it at the center. You know, your question about the square is going to be interesting in a second. Step 1, let's calculate h of z naught. Okay, that would be, by definition, the integral from 0 to 2 pi, 1 over, let's see, that parameterization was z naught plus r e to the it minus z naught. And then the parameterization, the derivative, is I r e to the it. dt. That's the z prime of t. The derivative by the chain rule that I showed you some days ago. Okay, and a miracle happens here. The z naughts cancel in the denominator, and then the r's cancel and the e, the it's cancel, and this boils down to the integral from 0 to 2 pi. Let's see, the only thing that doesn't cancel is the I. And that's 2 pi I. Okay. That's kind of simple from just direct calculation. Step 2 is that we can differentiate under the integral sign. So this is by homework number 1. H prime of A is d by dA of integral around the circle of 1 over z minus A dz. And that function 1 is continuous. So this is homework 2, problem 1. The derivative of that thing I can calculate by differentiating under the integral sign, basically. Let's see, that would be, what would it be? It would be the integral, let's say z to the minus 1, so a minus 1 would come out. And then I'd get 1 over z minus a squared, and have to differentiate with respect to a, another minus 1 would come out. So problem 1 says I can differentiate under the integral sign. In the a variable. And now the aha moment is that's the derivative of something in the z variable. Okay, so this is equal to, call this an aha. This is equal to the integral of a derivative in the z variable this time. So d by dz of minus 1 over z minus a. and being the derivative of something, and we're going around a closed contour, that's going to be a big fat 0. So this is minus 1 over z minus a evaluated between the start and the end. And it's a circle, so those are the same. And so that's a big fat 0. So h prime of a is that's 0, identically 0. So h prime of a is identically 0, and that means h is constant. But the constant h of z naught is equal to 2 pi I, so that constant is identically 2 pi I. So that gives me the Cauchy integral formula. Let's see. If you do that problem number 1 trick multiple times, you get higher order Cauchy integral formulas. Formulas. Okay, we have f of a is equal to 1 over 2 pi I, integral around the circle of f of z over z minus a dz. If I differentiate it once, I get f prime of a equals 1 over 2 pi I. I'm differentiating under the integral sign once. Here I'd get z minus a squared dz. And I do it again and again. Let's see. By the way, I can repeat this. And so the second derivative, I guess I'll tell you, as you repeat it, you would get that the nth derivative at a is n factorial over 2 pi I, repeatedly differentiating under the integral sign, over z minus a to the n plus 1 dz. And so you can do that again and again. And the proof of doing it again and again is very similar to your homework problem 1 calculation. And this is exactly how you see that that F analytic implies F prime is analytic. Because those formulas I can differentiate indefinitely. Guess I'm running out of time. Any last minute questions about anything? Yeah, so that's amazing that we can get the Cauchy integral formula and suddenly start deriving all these mind-blowing properties of analytic functions. By the way, this implies that F is equal to U plus IV, where these U